Alright, so now that the first unit is behind us, we are going to move on to Unit 2, which deals with probabilities and probability distributions as their chief focuses. In this unit, a lot of the applied problems and motivating examples will be with the actual examples we work with themselves. Now, for those of you that finished the test, you might find this meme to be rather appropriate. Hope you get a good laugh out of it. So, we're going to start with the view definitions, relatively short and quick, and then we're going to move on to visual displays for students who are visual learners, and then the examples, laws, formulas, etc. So when we discuss probability, mathematically it's from 0 to 100% inclusive. Now, in common parlance, we might say, I am 120% confident that the Patriots are going to lose the Super Bowl. Or you might say, I am 200% sure that I'm going to fail this test. When we say that, we don't literally mean you're going to fail the test so hard that you're going to fail it twice in one sitting. What we really mean is we are completely and totally sure that it will occur. On the other extreme, suppose that you're going to pick your parents up from the airport, they give you a call, they say, you're going to be here within 5 minutes, and you say, I am negative 25% sure that I will be there in 5 minutes. Now, you don't literally mean you're going to break the fabric of space and time and somehow go backwards into the 1930s or anything like that. You're essentially saying 0% chance. So it is important that you convert your English parlance into the mathematical concepts here, because otherwise you can get some very funky mathematical results. Now, when dealing with these probabilities, sometimes we'll have discrete outcomes, sometimes continuous outcomes. Say when we're talking about discrete outcomes, we're rolling a die, a fair six-sided die, 1, 2, 3, 4, 5, 6. That would constitute our sample space, the set of all possible outcomes. So let's suppose you're playing a game of Settlers of Catan, and you're rolling 2 dice, and for whatever reason you're a goober, and you have 3 cities all around a 12. Don't know why you do that, but hey, we've all done goofy things at some point before. In this case, we could say P of A, where A is 12, is the chance of A rolling a 12 occurring. On the other hand, suppose that your friends really do not want your goofy bet to pay off, so they might want P of not A, so not getting a 12 being the case. Here we have the tilde, which on your keyboard is Shift and then the key on the top left that's below Escape. Now, if you're in computer science, you might be familiar with the exclamation mark, so not A. The reason why we don't use that notation in this course is because the exclamation mark will be used for an operation called the factorial a little bit later in this unit. So instead, we will use the tilde. So if it's tilde A, that means everything not A. So in the case of rolling a 12, if we do not want a 12, then that would be a 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11. This is what's known as the complement of A, so quite literally everything not A. As another example, if you have 12 cards in your hand in Settlers of Catan, your hope is that a 7 is not rolled lest you flip the table over and go jump out the window, because you're finally about to win, and now everyone's suffering has to be prolonged for another 5 minutes. Unless another 7 is rolled, in which case you have to prolong that for another 5 minutes. Next thing you know, the sun's already risen. In that case, your complement of A, everything not A, would be 2, 3, 4, 5, 6, 8, 9, 10, 11, and 12. Now, in that case, you could add up all those probabilities, or you could use something called the complement law that we'll discuss in a little bit. Now, when dealing with these events, we have independent and dependent events, and these give rise to different probability laws and rules. When we're dealing with independent events, one event occurring or not occurring does not have a bearing on another event occurring or not occurring. Now, some people make a mistake known as the gambler's fallacy, where they think something is on a hot streak, and so therefore it definitely must occur again, or there's no possible way it can occur again. Well, if we take, say, just one die, and we roll it once, just because we've gotten a 6 3 times in a row, that doesn't mean we're guaranteed to get a 6 on the next roll, or guaranteed not to get a 6 on the next roll, because at least, in theory, each die roll is supposed to be independent. On the other hand, we do have some circumstances where one event happening, or not happening, changes the chances of another event happening. So for example, let's go to a game of Monopoly, and let's suppose you're heading down death row, the greens and the blues, and your goal is not to land on Boardwalk or Park Place. And you're starting from the space right before jail. Suppose that you roll a 6. That'll put you on the railroad. Well, in that case, if you roll a 2 or a 4, you'll land on those blues. However, it is no longer possible to land on the greens. And so, therefore, your roll of a 6 changed the probability of you landing on a green on the next turn. Now, if we were just considering the roll in isolation, that in and of itself is one roll. If we want to specifically focus on that one roll, let's consider the 2 dice in that roll. Suppose your goal is not to roll a 12, land on Boardwalk, and get immediately bankrupted. Well, in order to get that 12, you need to roll 2 6s. Suppose that you, in the interest of significantly increasing the drama, decided to roll 1 die at a time. If you roll the first die and it comes up as a 1, it's no longer possible for you to roll that 12. And so that is, if we treat these 2 dice separately and then add them together, now our final result can be dependent on what we initially get die by die. Went up dramatically. So that is the idea behind independent and dependent events. Something important to consider is just because we're on a hot streak or a drought, whether it's with gambling or something else in life, that doesn't necessarily mean there are nefarious forces acting behind the scenes. Could be, probably not. So, in the example of rolling that 12, 1 die at a time, this gives rise to conditional probability, and this helps to relate our independent and dependent events together depending on the circumstances that arise. So for example, suppose we're rolling 1 die at a time and we're asking the probability that our 2 dice sum up to a 12 given that our first die was a 1. Well, in that case, the answer is going to be 0. Because if your first die is a 1, even if your second die was a 6, you still can't get 12. On the other hand, what's the probability of getting that 12 if our first die was a 6? Well, now it just depends on whether or not the second die is a 6, equal probability, 1 out of 6. And so this bar, this is what some of you might recognize as the absolute value bar. On your keyboard, it is shift, and then I believe that's the /. It's the right above the enter key, and that denotes conditional probability. So the chance of A happening, assuming that B has occurred. Sometimes you can slightly flip it around, and you can say P of A given not B. But it's still the same idea. Conditional probability is one of the most important concepts both in this course and beyond that. Even if you do not become a math or stats major, or you don't major in anything related to STEM, you're still going to see conditional probability come up a lot in life, and if you have a good understanding of it, then it'll allow you to process the world in a way that'll give you a better understanding of it and what's happening around you, as opposed to somebody who has their head in the sand. So with that, let's now get on to some visuals. We'll start with the example of flipping a coin. Here we have a tree diagram, briefly touched upon in the previous unit. Let's suppose we just flip the coin twice. In the case of flipping the coin twice, we can get a head or a tail. Let's assume that it's fair. Suppose we flip a head the first time. The second time, we could still get a head or a tail. Those are independent of each other. But now, let's suppose I asked you for the probability of getting 2 heads. From the outset, we have 1 out of 4 possibilities, so 1 out of 4. And this is a visual one. We'll get to the computational reason why a bit later. On the other hand, let's suppose you rolled a head the first time. Well, flipped a head the first time. In this case, this whole bottom part is no longer possible because you didn't roll a tail the first time. So in effect, suppose I ask you for the probability of getting 2 heads given that you already rolled a head on the first time. In this case, it's all down to the second flip. If you get a heads on the second flip, you're good to go. So it's now down to 1/2. So that is a tree diagram illustration of conditional probability. We have some more visual examples of these definitions as well. So here's a visual example of the complement law. Oh, there we go. So with the complements, suppose that this rectangle right here constitutes our sample space. And in particular, this right here is the event A that we're interested in. The complement of A is going to be all of the rest of this, everything else. Therefore, by looking at this, if you add up A and the complement of A, that is their probabilities, it's going to have to add up to everything. And that's going to be one of the probability laws that you'll see in a moment. I'll come back here to reference that in case you're a little bit confused. Our next visual example is what we call the intersection of two events. The probability of A and B occurring. So converted into English, this says A and B. The probability of A and B occurring is their overlap. For example, suppose that we are out in this area. If we're out in that area, then neither A nor B have occurred, so there's no intersection. On the other hand, let's suppose that we're in this area. Well, maybe A and B has occurred. We're not sure. The same goes if we are in this area. If B has occurred, maybe A and B will occur. And likewise, if both of them have occurred, we have this overlap and we have the P of A and B. So let's consider those possibilities and how this can inform us with the complement law, which you'll see this formulation of P of A and B showing up in for the conditional probability law. That is, I'm going to give you part of the visual derivation for where the conditional probability law will come from. Think of it this way. Suppose we're considering a P, let's switch the color, a P of A given B. In order to have a P of A given B, by definition, we must have both. You can't have A given B unless you have A and B. So therefore, this formula at some point is going to have to involve our intersection. So this is why we have this notation for intersection, mostly because we'll need it for the definition of conditional probability. Next up, we have disjoint, the two events that are completely and totally independent of each other. They're mutually exclusive. The reason why is because, as you can see, there is no overlap between these two whatsoever. Obviously, if we're outside of both of them, then you can't have both. If A has occurred, then you can't have B because we're not in the yellow circle. Same idea goes with B. If two events are disjoint, then their conditional probability is 0. And then we have what's called the union. And this one is a bit more intuitive. We have U for union. In this case, it's A or B in the computer science sense. Converted to English, this technically means A and or B. If you have taken a computer science course before, then we can just put or and that'll register. But for a lot of students, when they hear or, they think one but not the other. The union means at least one of these. It's easy to remember the difference. We have U for union. So U for union and the upside down U for intersection. So as an example, suppose we're outside of A and B. Well, then neither has occurred. The union, therefore, has not happened. On the other hand, suppose we got A, but we didn't get B. Well, that's A or B, so we're good to go. Suppose we got just B. Well, that's A or B, we're good to go. And if we got A and B, that is A and or B, that's good to go. And so this is why this whole area constitutes our union. We do have a formula for getting the union of A with B, and we'll come back to that in just a moment. So now let's specifically look at this one. This one less so introduces a new definition and more so helps us understand where our formula for the union is going to come from. Let's think about it this way. Here we have the probability of A occurring. So we have this piece, and to change the color, we'll have this piece. So now what about B? That'll be both of these. So with the case of B, we will have this piece, and, we have this piece. We have double counted. So when constructing the conditional probability formula, we had to consider A and B. When constructing the A or B formula, we have to be concerned with the double counting of the overlap. So as you'll see in the formula, we're going to be subtracting that overlap from our computation. So now that we have the visual examples, let's get to the probability laws. You will need to have all of these for web work and the Unit 2 test. So I can go ahead and, technically speaking, put this into a box. As very important. And let's make that better. Come on. There we go. You're going to want to have these written down. Let's go part by part. We're going to start with this first formula. We have P of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Here's that overlap to show. So what we're looking for is the probability of A or B. That is, we're looking for the total value of this area. So, in that case, we can add the probability of A, which is this. That's our first part, right here. We can then add the probability of B, which is this area, and that is this. But because we've added both circles, we have included the overlap twice. And because we have included this overlap right here twice, this A and B, we must subtract it. Not because it isn't included, but because we double counted it. Now, let's suppose, coming back up here, that A and B are disjoint. They're independent. They're mutually exclusive. If that's the case, then there is not any overlap to speak of. That is, in this case, we have P of A and B is equal to 0. If that's the case, given that they're disjoint, then we get a simplification. And that is our first shortcut. This one right here. If A and B are independent of each other, then there's no overlap, meaning you wouldn't have to worry about the A and B part of the equation. So, we'll come back to this in a moment. That is our first formula. To convert to English, this first formula right here is the same thing as saying at least one of them. So at least A or at least B. Could be both, as long as we get at least one of them. This next one right here is the conditional probability formula. The probability of A given B is equal to the probability of A and the probability of B divided by the probability of B. You might ask yourself, wait, where did this P of B come from? Earlier, we gave the visual reason for why we're going to have the P of A and B. Because if we have A given B, this means you have both. So we're going to have a P of A and B. So you might say, well, then where did this P of B come from? Here's why. Let's come back up over here to this intersection. If B has already occurred, then we're limited to this. This remainder, all of this, can't happen because B has already occurred, meaning that everything else is out. This is all gone. We can't have it. We cannot have any of this. So therefore, we restrict our new sample space to just B. And so therefore, if A has occurred, given that B has occurred, we have the overlap, which is A and B. This is why we divide by P of B. In the case of the conditional probability formula right here, I'll zoom back out. The way we describe it in English is usually with the word given. So A given B. So to convert to something that's more understandable, what is the probability of a customer being satisfied given that it was shift 2? Or what is the probability that a clothing product is mismade given that it came from this factory? That's what conditional probability is for. And it's for when something has already occurred or is assumed to have occurred. Given is the most common word you'll see. If you see the word given, that is pretty much a dead giveaway, pun intended, of conditional probability. The word assumed is the next most common one you'll see. So, what is the probability of a shirt being defective, assuming that it came from this factory? Next up, we have the complement law. The probability of A plus the probability of not A is equal to 1, or 100%. That is, A and everything besides A have to add up to everything under consideration, because then otherwise we're missing something. There are many different ways to say this complement law. I'll zoom out a little bit. There are many different ways to say the complement law. Obviously, the word not. That is the most common one. On the other hand, suppose we said at least 1, which is greater than or equal to 1. Well, that's just saying not 0. So at least something. Another way of saying it is if we're dealing with our sample size. If we say below the biggest number, so less than n, that's everything besides n. Everything besides the biggest thing. Not everything. In the case of the complement law, coming back up to our display here, if we add up the probability of A, which is this, plus the probability of not A, which is this, by definition, they add up to the whole rectangle, which is 100%. And then we have the summation law. P of I is just a given probability. So the sum of all of our probabilities must add up to 100%. Because if it doesn't constitute everything, then we're missing something. Well, you might look at this and say, well, duh, what's the point? The usefulness in this is if you have all of the probabilities except for one of them, because that means you can add up all the probabilities you do have, subtract those from 1, and get the one you're missing. So this summation law is most useful when you have the probabilities for every single outcome except for one of them. So now let's go back to those shortcuts that I briefly mentioned earlier. We'll start with the second one, and this is for one trial. So say flip a coin just once. Not multiple times, just once. This assumes that our events are independent of each other. That is, there's no overlap. In that case, if there's no overlap, then we could remove the P of A and B from the formula and just get this. So let's suppose I asked you the probability of A occurring is 0.3, the probability of B occurring is 0.4, and the probability of either or is 0.7. You could immediately conclude that the two events were independent of each other because they both added up to that 0.7, meaning there was no overlap. So the main use of this second law for shortcuts for independence is that you can use it backwards to figure out if two events are independent of one another or dependent on each other. The other one is if we have multiple trials. So let's suppose we have events that are independent of each other. If we have multiple trials, then we don't have to worry about any overlap messing things up. So suppose we flip the coin the first time. 50-50. No matter what we flip on that first coin flip, the second time we flip the coin is completely and totally independent of the first time if it's a fair coin. And so therefore, we can just simply multiply the base probabilities onto each other. Again, this only works if we have multiple trials for independent events. You'll see with the binomial distribution, we're going to use this formulation. With the hypergeometric distribution, we can't quite do that. But more on those as we get to them. So, in the case of this first shortcut, the English is X then Y or back to back. So heads then tails, back to back. So now that we have these laws, let's start applying them. So we're going to go to a large number of practice examples. So you can take a moment to work each of them out as we get to them, and then we'll go over the answers. Many of them have layperson shortcuts, which are completely fine to use, but with all of them, I'm going to explain both the, what you might call common sense explanation, and I'm going to use probability laws as well, so you can get practice with both. By having both solutions, I hope there's at least one that will make sense that you're able to understand the material. So with that, here is our first example. If you would like to take a moment to do so, you are welcome to. So, let's start with the first one, the probability of getting at least one head. So P of greater than or equal to one head. In this case, that would be the probability of one head plus probability of two heads. But think of it this way. Remember, greater than or equal to 1 is the same thing as saying not 0. So that's the complement law. So 1 minus the probability of no heads. So that'll be equal to 1 minus this probability. How do we compute it? Because it's a 50-50 fair coin, there's no overlap between heads and tails. 50 plus 50 is 100. There's nothing else. We can't have overlap. Since there's no overlap, they are independent events, meaning we can use the independence shortcut for multiple events. So if we get no heads, that's the same thing as getting tails twice. The probability of getting tails twice is equal to 1/2 times 1/2, which is 3/4 when you subtract it. So the probability of getting at least one head is 3/4. Now let's move on to part B. For part B, the probability of getting greater than or equal to one tail is equal to 1 minus the probability of no tails. It's the same logic. And that is where the math converges with common sense. We just get the chances of getting these tails and knock them off of 1. So 1 minus 1/2, because getting heads the first time, and then heads the second time. Because common sense tells us if we're getting at least one tails, then we couldn't have gotten heads both times. Maybe once, not both. So all we have to do is just exclude the possibility where we get tails both times in order to get tails once, which is also 3/4. Now, let's get to part C. If we have at least one of each, that is going to be equal to the probability of getting heads and tails, so heads first and then tails, plus the probability of tails first and then heads. In this case, if we have heads and then tails, that's equal to the probability of heads times the probability of tails. Oh, come on. The clicker does not seem to want to cooperate. And then the probability of tails and heads is the same as the probability of tails times the probability of heads. In this case, probability of heads is 1/2. Probability of tails, 1/2. And then for our second one, probability of tails, 1/2. Again, 50-50. Plus the probability of heads, also 1/2. Times. And so that will be 1/4 plus 1/4, which is 1/2. And finally, for part D, what's the probability of landing on its edge at least once? 0%. Because if heads is 50-50 and tails is 50-50, that adds up to 100%. There's nothing left. And if you don't believe me, think of any time in your life where someone managed to land it on its side. Hasn't happened because of the laws of physics. It's really, really hard to do in non-controlled circumstances. Even in controlled circumstances, it's pretty hard. So, with that said, let us now continue on to our next problem. Fun fact, if you're wondering why the mouse is moving off a bit to the left, that's because the recording software is on the separate screen, so that way it's not out here in the open blocking your view of the whiteboard. So now we have this next one. Go ahead and take a moment to solve this one, if you would like to. So in this case, if you're a college grad with computer skills, that means we're looking for the probability of being a college grad, so we'll just say COLL since we already have a COM, and someone with computer skills, so comp. I could put COM, but someone's probably going to misinterpret that. So this is going to be equal to the probability of someone being a college grad times the probability of having computer skills. Here's the reason why we can do that. Although it's technically just one person, we have two trials on one person. Because you could have someone with computer skills who isn't a college grad. You could have someone who is a college grad who doesn't have computer skills. So if these two characteristics are independent, then that means it's going to be 0.4 times 0.3, which is 0.12. Now, at this point, you might say, wait a minute, why isn't it 0? If the two characteristics are independent of each other, then P of A and B is equal to 0. So why isn't the answer 0? Here's the reason why. Because it's not one trial. We're not asking, given that somebody only has one trait, what's the probability of being a college grad and having computer skills? We're saying, given that they have two traits, with these as the possibilities, what are the chances they have both? So it's a small little quirk, and you'll see with a lot of the materials in this course that the wording can very much so change the whole answer. In the case of, say, the SATs, the ACTs, or AP tests, they will oftentimes love to throw in a small word, not bolded and not underlined, that causes the whole answer to be changed. In this course, I promise you, those such words will be bolded and or underlined to make it very clear. So, with that said, let's take a little bit of a breather, because there's a slight problem. In these examples, we had complete information. We had all the numbers. We just had to do computations associated with them. But let's move into the real world for a little bit now. What happens if your coworker is an idiot? It happens. People do stupid things sometimes. What happens if you don't have all the data you need? What happens if somebody sends you an Excel workbook and you're missing a bunch of the entries, or, God forbid, a whole sheet? If you're missing a whole sheet, so you're just missing nearly everything, we have ways of dealing with that in Unit 3. In this unit, we're going to consider the possibility where you're missing some of the entries. So you have some of the data, but not all of it. So Unit 2, we'll talk about some but not all the data, and in Unit 3, we're going to assume that we know pretty much nothing. So let's consider Case 1, the possibility where you have some but not all of the entries. In many of these cases, you can use logical deduction to get your remaining entries so that you can finally perform some analysis of the data. For anyone who has played Sudoku before, or any kind of logic game, this will be very familiar. But some students haven't, and that's fine. I'm going to go through the process from the basics so that everyone is working from the same playing field. If you've played a game of Sudoku before, if you've done a logic puzzle before, you're going to find this to be extremely easy. So let's suppose we have a table where we're missing a large number of the entries. As long as we have at least half of them, we can get all the remaining entries back. So even if your coworker is an idiot and forgot to put the remaining data values in there, or even if someone you're working with just forgets to send you a bunch of the data values or survey a bunch of the data values, you can still oftentimes use logical deduction to get those remaining data values. Now, if we went over every single possible case of logical deduction, it would turn into an entire degree program, which the Department of Philosophy probably already has. So we're going to stick with the logical exercises that are more so applied. So, at the top here, I have a recursive plan for solving partially filled tables. Again, if you've done a Sudoku puzzle before, a logic puzzle before, or anything of the sort, you probably don't need this. But some students haven't, so that's why it's here. What you want to do is in your table, go through all of your rows and columns. See if you have a row where you're only missing one entry. And this is assuming you have your totals. If you're only missing one entry, then if you add up all of the entries, they must equal the total. Meaning you can just use a simple, basic algebraic manipulation to get the data value you're missing. And in the case of a calculator, it's an extremely simple computation. Once you do that, you put that data value you just discovered back in the table. Then, do that with all your rows. Do the same thing with your columns. So now go through your columns and identify all of your columns with one missing entry. In that case, same idea. All those data values have to add up to their total. Once you've done this, it's possible you might already be done immediately. It's more likely you're going to have to go through again. Now that you have newly discovered information, you can do it again. Go back through your rows and your columns again, because there's going to be at least one of them you can do. And so you keep doing this recursive formula up until you have all your data values. In this case, it can be very helpful to do it with an example. So in this example, I am going to use red for our first step. Have some color coding, make it easier to see what's going on. Let's start with our rows. In our first row, we're missing 2 entries, so tough luck. In our second row, we're missing 3 entries. Tough luck. In our third row, 2 from the second. We're missing 2 from the third row. Tough luck. But in our fourth row, we have all but 1 entry. So we can do something there. In the case of our columns, we have everything here except for the first. So we can do the under 18s. We have nothing in the 18 to 65s. As you can see here, apparently whoever did the survey forgot to tell us what the non-retired adults were. Oops. In the case of the seniors, we have everything but one category. And in the case of the totals, we have everything but one. If you're wondering what this study is, this was a study dealing with cholesterol levels as they related to weight and life expectancy. Obviously, when it comes to weight, you can have a healthy weight, you can be a bit overweight. And then there's a phrase from the comedian George Carlin, who is one of the greatest comedians of all time. He had a nice phrase to describe them. I suppose you could use a one-word name to call them, but I think we could all agree that lumbering through the malls like a fleet of interstate buses is quite the image. And no matter what type of person you are, that's something that is quite the picture to think of. Regardless, let's get back to the math. This is not a comedy class. We'll throw a few jokes in there every now and then just so that you can keep a little bit perked up and not get bored to death. So, we'll start with the rows. In this row, we have the 20, the data value we're missing, and the 20 have to add up to 100. So therefore, the missing data value is 60. In the case of our columns, we can do the under 18, the over 65, and the totals. So let's get through all of them. In the case of the under 18s, we have something we're missing, plus the 4, plus the 1, which is equal to 20. So therefore, we have 15 of them here. In the case of the over 65s, we have 10 plus what we're missing, plus the 1 is equal to 20. So therefore, what we're missing is the 9. And then finally, for these totals, we have 40 plus 50 plus what we're missing is equal to 100. And what we're missing is 10. Now that we've filled out all of our rows and columns for our first round, let's go to round 2. And I'm going to use blue for round 2. We have everything in the first row except for 18 to 65. Same for the second row. And same for the third row. So we can finish out our table. We have 15 plus what we're missing. Oh my goodness, the mouse is uncooperative. Let's try that again. How about we type it instead? Because this mouse does not seem to want to cooperate. We have 15 plus what we're missing plus the 10 is equal to 40. And so therefore, what we're missing is 15. In the case of the next row, we have the 4, what we're missing, the 9, and that all has to add up to 50. So therefore, that question mark is 37. And for this last one, the 1 plus what we're missing plus the 1 is equal to 10. And so therefore, this is going to be 8. And something that is not going to come as a surprise to anybody at all, newborns and seniors tend to be at a healthy weight. The reason why is simple. When you're a newborn, you haven't been here long. And if you're a 90-year-old, you can't really afford to be running around somersaulting through Walmart. So that is the general idea for how we do the logical deduction. So, to give you practice with logical deduction, I have an example here, this time with letter grades. Sometimes you might have a professor that is very secretive with their letter grades and only gives you partial information. I promise to you, I will be clear and transparent in this course with all letter grades. Sometimes you're just not going to have a professor that's clear and transparent. So here we have some partial letter grade entries for a series of courses from the year 2020 during the pandemic. A's, B's, C's, and F's. If you'd like to, go ahead, take a moment to try to work this one out, and then we'll go over the answers. And like with before, we are going to use red to describe our first iteration and blue for the second. So, going by rows and columns, we can get 3350 and tough luck. Additionally, when going by columns, we can do the A's. So here we didn't have quite as good luck as the previous time. We were able to fill out much more columns at once. So in this case, for our first column, this is very simple and straightforward. 9 plus 9, plus 8, plus 9 plus 16. This is equal to what we're missing, which is that 42. That's about the easiest you could expect. And then for the rows we had up here, we had the 9, the 17, what we're missing, and the 2, which is equal to 36. And therefore, the C is 8. Technically speaking, because we do rows first, when we switch to the columns, we could do this one while we're at it. So technically, this is a part of the first step, so I'll keep it in red. Because again, we did the rows first. If you do the columns first, you'll technically have a third round of it, but it's the same amount of work. Here we'll have the 8 plus 6 plus 8, well, plus what we're missing, plus 8, is equal to 28. And what we're missing is 6. Again, this will be your first or your second iteration, depending on where you started with. Now that we have those, we have this other column over here. So let's get it. We had 36 plus what we're missing, plus 35 plus 52 is equal to 149, and that which we're missing is 26. Now, let's move on to round 2. We can't do anything else with the columns, but we can do a lot with the rows. We can now do 1300. We can do 3350.02. And we can do total. So let's get started with those. In the case of 1300, we have 8 plus what we're missing, plus 6 plus 0 is 26. And that which we are missing is therefore 12. Blue for round 2. For 3350, same idea. Well, 3350.012, that is. 9 plus what we're missing, plus 6 plus 6, 35. Therefore, what we are missing here is the 14. And then, for our final row, we have 42 plus 70 plus 28 plus what we're missing is 149. And therefore, what we're missing is a paltry 9. Because we do the rows first in the recursive algorithm, we can now do all these columns in the same step. Again, if you did your columns first, this would technically be your third round. Regardless, now for this B's column, 17 plus 12 plus 14 plus what we're missing is equal to 70, and therefore what we're missing is 23. And finally, for our F's, which I assume you're hoping not to get in this course, 2 plus 0 plus 6 plus what we're missing is 9, which is very clearly 1. And that is the logical deduction for the table size that you'll see on the Unit 2 test. So now, let's bring it all together. We're going to combine the probability laws with logical deduction. We're going to have you, in our applied example, our motivating example, be the manager of a shirt factory. And you want to see if your shifts are behaving a bit differently depending on the time of day. Now, I will admit, the first time this lecture was given, back in 2021, there was a typo. This word was missing the letter F. It was quite a comical moment in class, slightly embarrassing, but rest assured, it is spelled correctly here. So, suppose that you are a manager of a shirt manufacturer, and you want to see if there is a relationship between the shifts and the quality of the shirts being made. But you have a problem. You only have so much time in the day, and your supervisors are not all that great at gathering data. Maybe they're bad at counting, maybe they're not good at reporting. So you as the manager have partial information. Maybe when you graduate from Texas Tech, you'll be managing your own company. And performing analyses on the shifts at your workplace can be helpful. So what I want you to do is, given this partial information, fill in your empty entries by using logical deduction, and then answer these two applied parts. So, for this problem, to answer a slight question, you might say, oh, what if I do a better job with my survey? Well, there's another catch to this. Suppose that your coworkers, managers, and supervisors are all doing a good job of collecting data. Technically speaking, you could collect only half the data and use logic to get the remaining data without having to spend any more money. And as any of you who have already taken a management course know, the saving of money through associated labor and overhead costs will obviously increase the profit margins of your company. So in this case, we will, once again, start with red in order to explain the deduction. We're going to need 3 steps this time now because we really have a limited amount of data. Whether you start with the rows or start with the columns, everyone will have the same first step. You cannot start with the rows for any of these because each row is missing 2 entries. You cannot start with 3 of the columns. Well, technically you can start with 2 of them, although you'll start with the first. You can't start with 2 of the columns because 2 of them have blank entries. There are only 2 options. You have to start with your columns, and you have to start with shifts 1 and shift 3. As you can see, shift 2 is absolutely horrible when it comes to reporting data. And unsurprisingly, as you'll see, both of our questions are about shift 2. Spoiler alert, if you have a shift that's not good at reporting data, maybe something's going on there. Something that might help you out. In this case, 240 plus something is 250 will obviously be 10. 139 plus 11 is 150. And with that, it's time for round 2. Don't worry, it's not a boxing match. You're not about to get punched in the face. If you want to punch yourself in the face, you can, but I have nothing to do with it. In this case, with our rows, we can now do the second row and the third row with data values, that is. 10 plus 9 plus 11 is 30. And 250 plus something plus 150 equaling 600 means we have 200 here. Thus, for our final step in green, 191 plus 90 is equal to 200. And 570 plus 30 is equal to 600. So now, let's answer the questions. What proportion of the shirts were perfect or made by shift 2? So we are asking for the probability that a shirt is perfect or made by shift 2. I'm going to move this down just a little bit so we have more space to work with. This is going to be equal to the probability of a shirt being perfect plus, oh, come on, plus the probability that it was made by shift 2. Because these events are not necessarily independent of one another, we have to subtract the overlap. So now the full overlap law, the full union law applies. And by union law, I mean math, not in terms of governmental policy. This is a math class, not a class on U.S. federal government policy as it relates to Supreme Court cases on unions. We ain't touching that. So this is equal to the probability, perfect, and shift 2, so we account for the overlap. The probability of a shirt being perfect is simply all the perfect shirts, 570, divided by the total number of shirts, which is 600. Plus the probability that a shirt was made by shift 2. Shift 2 made 200. So we have 200 over 600. And then we subtract the number of shirts that were perfect and made by shift 2. 191. So 191 over 600. Joining up, oh my goodness, that is not a pretty 6. Joining up all of our denominators, divided by 600, gives us 579, adding up those numerators, which, if you wanted to put it into decimal form, you technically could. So you could take this 579 over 600, which is roughly 96.5%. However, again, you can put the fraction into WebWork and it'll round it for you. On the test, everything will be formatted in the same way. Finally, given that the shirts were perfect, given that the shirts were made by shift 2, what proportion of the shirts were perfect? In this case, this is probability that it was perfect given that they were made by shift 2. Don't flip them around. This is going to be equal to the probability that a shirt is perfect and made by shift 2, as per the conditional probability law, divided by the probability that it was made by shift 2. The probability that it was perfect and made by shift 2, we already got that, 191 over 600. And the probability that it was made by shift 2, we've already gotten that as well, 200 over 600. Therefore, these two 600s are going to cancel each other out. And therefore, we're left with 191 over 200. Now, you might ask, hold on, couldn't I shortcut this by using the table with a little bit of intuition and common sense? The answer is yes. So in the case of the first one, it says perfect or made by shift 2. So everything in this row plus everything in this column. As you can very clearly see, we just have to get rid of the 191 overlap. So we have the 200 and the 570, knock off the 191, divide by 600, and we're good. In that case, using this visual approach, you can save a little bit of time, but do notice that you have to, through your computation or looking at it, take care of that intersection. Because if you don't, then you're going to be counting an overlap twice. In the case of a second one, given that they were made by shift 2, so we're only considering this rectangle, what's the probability that they were perfect? So 191 over that 200. This is another reason why using the logical deduction can help, because if you have the full tables, the computations simplify a good bit. On the test itself, you will have a logic table you have to work with, and you'll have to answer a series of questions associated with it. There will be a total of 8 blanks in the logic table. It will be a similar size to the previous example. The practice test has one as well. You'll be able to enter in those numbers. Partial credit will be enabled. There will be then 4 questions about the numbers in the probability table. 2 of them will be, well, not probability table, in the data table. 2 of the numbers will be probability questions, like the ones we've covered here. The other 2 will be ones about expected value, which we're going to cover in the next lecture. With that, we have completed all of the material for today's lecture. In the following lectures, we're going to cover discrete probability distributions and continuous probability distributions. So we're going to dive a bit more into some specific circumstances and how they are going to apply to situations you might find in your life. So with that, have a great rest of your day, and I'll see you in the next lecture.